Okay, coming to the floating point types. Floating point types are float and double. Suppose I specify a literal like this. What's the type? Default is double. Fine, by default it would be double. If you want it to be specified as a float, have a suffix of f, upper or lower case. And we understand all this, right? Okay. Now how floating point values are stored, or okay, before that, let's say we have, let me write a small piece of code. I'll try with, let's say, a double. It may be double, it may be float. A equals, I'm putting value 75 there. Okay, I have double, B equals 0, and then I say double, C equals A divided by B. Fine. What's the value in C? Even in C language, it's the same. Okay, the results are same. What's the value in C? What's the value in C? There's no error. There's no error here. When you divide something by 0, what's the answer? Infinity. And that's exactly what is there in C. C has the value infinity. Fine. If it was minus 75, C gets a value minus infinity. Okay. Fine. There's no error here. Fine. Only yes, in case you are not using double, you are using an int value, int type. Fine. The whole numbers, int long or byte short, int long, or the char type. Char is also numeric. Okay. So if you use any of those, in that case, it's an error. Right? Because the result would be infinity, but as far as these whole numbers are concerned, and their representation, they use 2's complement, they have those fixed values, fine, equidistant, fine, distance of 1, okay, fine, I am looking at the number line, so you have a fixed portion of the number line, that's it. Okay, what about the float and the double type? So for float and double types, there is a different, it's not a 2's complement, it uses mantissa exponent. Okay, let's see what exactly is happening there. What is done here? Okay, the float and double, they follow what is known as a standard. The standard for them is IEEE 754. Fine, refer to that IEEE 754. And this is having, it says single and double. Fine. There are two types in this, single and double. Single means 32-bit and double means 64-bit. Okay, so according to this standard, what you have is, whatever the number of bits are, fine, I am not giving the exact numbers, let's say 32-bit. So in that, you have bits from, bit position will be from 0 to 31. Your bit 31 is the sign bit. Okay, and then I think up to bit number 22, the next 8 bits probably, 8 or 9, yeah, 8 bits. Okay, they are used as exponent, and rest of the bits, they are known as significand. They use the term significand. When that's how the bits of your float are divided. Same way for double, the number of exponent bits are probably 12, I think. Okay, they are 12. Okay, that's the only change, and rest of the bits are, so instead of or 10, right, 10 or something, it has more exponent bits compared to there are a few additional exponent bits. Fine, and you can refer that IEEE 754. You'll know how many bits are there exactly. Fine. Now, one thing here is, according to this IEEE 754, the way it has been designed, if you have all your exponent bits set as 1, if all the exponent bits are set as 1, it does not represent a finite value. It does not represent a finite value. Fine. So in case you have all exponent bits as 1s, then let's look at the cases. What we have here is, we have representations for infinities. So infinity is something which can be represented with a float or a double type. Fine. So when you have a division by 0, yeah, it could be a positive infinity, a negative infinity. Okay, then it can be stored. If it is positive infinity, your sign bit is going to be 0. Fine. So sign bit represents a sign. Infinity means, if it's an infinity, exponent bits 1s and significant all zeros. If this is all zeros, okay, then it's infinity. All zeros for significant, all 1s for the exponent, that's infinity. Sign bit will decide positive or negative. Okay. Now what is 0 divided by 0? Suppose you had a 0 divided by 0. What's the answer? It's known as not a number. Fine. 0 divided by 0 is not a number. NaN. Fine. 0 by 0 is not a number. Okay. Our representation for float has an option of representing not a number, but there are so many not a numbers, because what you have is all exponent bits as 1s and any combination here other than all zeros. For significant, anything other than all zeros, that's not a number. Okay, they are all not a number. So anything like that, not a number. That's it. It's not a finite value. It will be an error. I don't have any representation for not a number. In int you only have things from, if it's an int it will be minus something up to that plus something. I don't have anything called infinity. I don't store anything called not a number. I don't store anything called positive or negative infinity. And there's no representation available for them. But in this IEEE 754, that's what they have done. They have said, okay, this is how we'll use it. Fine, this represents infinity, this represents negative infinity, this is representing not a number. So you have representations for all of them. Okay, fine. So you don't get error, okay, you get the value. And of course it will be interesting when you start comparing with not a number. Some value to be compared with not a number. Someone says, is A greater than C or C greater than A? Those are interesting things. We'll come to that when we look at operators, right? Okay. Yeah.
So can you please once again explain representation of 32-bit not a number?
Not a number? Okay, if it is anything, this is all exponent bits are 1s, and here If it is all zeros, it becomes infinity. Any other combination, so many of them, so many representations for not a number. Any combination, it's not all zeros, that's it. Any one bit is non-zero, it's not a number. Any combinations, yes, they are all not a number, so many represent, it's not a number, that's it.
If we consider the sign bit not a number.
Sign bit doesn't make a difference. All exponent bits are ones, this is not all zeros, not a number. If this is all zeros, infinity.
Can we print C?
Yeah,
Can we print C?
yes, you can print it. Even in C language, divide by 0 and see, print. But use double, not int. Fine, use double, even with C language. Fine, with C language, I think depending on your compiler, it might print. I've seen some compilers print INF and minus INF. Okay, NaN would be NaN that way. Fine. In Java, it prints infinity and minus infinity. And so someone prints a value of C there, right? And so experiment, you can experiment that way. But keep floating point type. Okay, now let's understand another concept here about the floating point types. These floating point types are not precise values. They are very imprecise. Fine. How? Yeah, point 333. Okay, 0.333 is something, maybe when you divide by 3 and you get something. That's even on even in our maths. Now I'm not talking about that maths thing. Fine. It is something which is the represented more by a fraction rather than by a decimals, right? But okay, ignore that. Even otherwise, is it 0.33333 that I can represent in a float? Can I represent the value? Let's leave that 0.333. Someone says, I have 7.9387. Suppose that's my number. You store this number. And you say, let me print this. And you may not get this number exactly. You may not get this number. Oh, I'm talking about smaller values here. But if you have larger values, you'll have still more problems. Fine. Let me show the problem first. Okay. Fine. I take the type float. Okay. And this is exactly what you can try also later. Float A equals, let me assign a value, but it's a bigger value, 1, 2, 3, 4, 5, 6, 7, 8, 9. I will not use a decimal. And there's no decimal also in this, right? But it is so imprecise at this level that when I print A, you know what it is printing? It's not able to store this value in a float. It's printing to me 1, 2, 3, 4, 5, 6, 7, 9, 2. If I reduce this value to by a few values, fine, it says I can't store anything between 7, 8, 4. 1, 2, 3, 4, 5, 6, 7, 8, 4. You go further. After that, I can only represent this in a float. A float cannot represent everything on your number line. Oh, your number line has infinite numbers, right? Okay. So let's see what exactly is happening here. And if you make a comparison, you got your number line. Okay, you got a 0. Fine, the 0 on the number line. Fine, not everything can be represented in a float, because what is float? Oh, it has got only 32 bits. How many different combinations can I have? 2 to the power of 32. But what's my range? What's my range? The range of the values which I am having, because I use that exponent form, I can represent real large values also by taking exponent. Fine, and therefore my representation here, the range, value range, is much larger, even larger than the long type. Long type is 2 to the power of 63. Fine, minus 1. Fine. Okay, so there are 2 to the power of 64 different values there, but here I have less number of combinations available to me, and many of them are actually consumed by NN. Many of those combinations here you can just remove. You don't have so many things available. And yet I am able to represent larger values because I follow exponent. And what's exactly happening here is, between 0 and 1, and between 1 and 2, between 2 and then 4 exponentially, between 4 and then 8, the number of values which I represent here, okay, this is exactly the same. Between 4 and 8, how many different positions can I take? That's exactly the same number of positions which I have between 2 and 4. There are exactly some definite points which are representable. In between, no, everything can't be represented, but there are infinite numbers otherwise. Okay, fine, but that's how that exponential thing is running. So what's happening is, when you are nearer to 0, your precision level is good. As you go away from 0, precision falls drastically, exponentially. Okay, and at this level, at a number which is as large as this, you can see what has happened. The distance between two representations is 8. It's not in decimals now. Here it would be in some level of decimals, but as you go away, the distance keeps on increasing. Fine, so floating point types are imprecise, should not be used for sensitive calculations, scientific calculations, and even commercial. Okay, so one thing, never use float, never use it. If at all you are trying to use, you may use double, it has at least better precision level. Okay, this has slightly better precision, but still that also would fall flat as the value increases. Fine, if the value is large, if you are dealing with large values, no, float and double would not serve any purpose. Fine. Okay, there actually are some classes available in the Java API. Okay, there's something called, we may have a reference to it later, big integer and big decimal. These are classes basically. Okay, fine, which are options available for large values, because long would mean you go only up to 18-digit number. Fine, 2 to the power of 63 is some 18-digit number. So if you have values, larger values, fine, you may be dealing with 100-digit numbers, you want to deal with them. How do we do that? You have classes called big integer, big decimal. Fine, so one thing, never use float. Fine, okay, you may use double, fine, sometimes, but don't use float. Fine, you understood what, that it is imprecise. Fine, why it is imprecise, that we understand now.